In the last class, we have in the main seen that the differential equations of one dimensional systems, we could see how these are obtained from the Lagrangian equation. Let us now go to one stage higher to the two dimensional systems. Two dimensional means two spatial dimensions. Now, let us take as an example a simple 2D system. Here is the constraint, a flat plane with two walls, and there are two masses. They are linked with a spring, and these are also connected to the walls by means of springs. And for the present moment, we consider these as frictionless surfaces. In that case, how we will define the generalized coordinates? Can you suggest? Simply, the positions of this. Okay. So, this is say q1 and this is say q2 measured from some kind of a datum, say here, all right. The moment we have written down these two as the generalized coordinates, so let us write now. In terms of these two generalized coordinates, we need to write down the kinetic energy and the potential energy. So, let us first write down the T, pretty simple, because this has say a mass m1 and this has mass m2. Let this be k1, k2 and k3. Then the kinetic energy is half m1 q1 dot square for the first one plus half m2 q2 dot square, simple. Okay. The potential energy V, the potential energy in this spring will be, yes, half k1 q1 square. This one is and yes, q1 minus q2. Okay. Any question?
So, we have taken q1 and q2 from which datum?
Here there is a question. Okay, let us for the sake of simplicity assume that for this spring q1 is measured from its unstressed position, and for this spring q2 is measured from its unstressed position. You could assume anything otherwise. What will happen is that these will have some constant terms which on differentiation will vanish, but this is easy way to write, that is why we assume that way. So, her question was, where do you assume the datum? Yes, that we could assume anywhere, but that would be a convenient way of doing it. So, the Lagrangian function is T minus V, that would be half m1 q1 dot square plus half m2 q2 dot square plus minus half k1 q1 square minus half k3 q2 square minus half, is it visible? Yes, k2 q1 minus q2. Now take the derivatives, sorry, the Lagrangian with respect to say q1, we will have to write the Lagrangian with respect to q2, we will have to write the Lagrangian with respect to q1 dot, and we will have to write it in terms of do this. From here it is pretty simple affair. You can see that the first one is this one would be minus k1 and yeah. Now here it will be minus k3 q2 plus here k2 q1 minus q2. Then with respect to the generalized velocities, it is simple m1 q1 dot and m2, these are the momenta, can you see that, q2 dot. The moment you have written down this, remember there would be two differential equations coming out of the Lagrangian formalism, one along q1, another along q2. So the differential equation along q1 would be d dt of dot minus fine. Now if you write down, it will be if you substitute m1, this fellow would be q1 double dot, because you are taking derivative with respect to time once again, and then this would be minus, let me copy from here this term, plus k1 q1 plus k2 q1 minus q2. Okay, happy? Differential equation along q2 will be, notice the advantage of this formalism, that simply by substituting q1 q2 you get the according differential equation. It will be just substitute this with change this to the equation with respect to q2 dot minus Lagrangian with respect to q2 is equal to 0. Substitute, you get m2 q2 double dot plus k3 q2 minus k2 q1 minus q2. So this is the first equation and this is the second equation along two different directions. Simple, we did not have to bother about individual bodies, and you can easily see that if there were n number of bodies, still we could do the same procedure pretty simply. Clear? Let us take another. Oh, we have already started doing one 2D problem the last day. Where were we? Let us see. Do we have? Oh, I lost the paper. So, that way that day the problem was we took a spring pendulum and our variables were theta, and if the total, when it hangs vertically, if the position is like this, then this distance was a. Is that visible? Yes. And here this distance was a plus r. That is how we have defined r and theta are the coordinates, and then we have already written down the Lagrangian function. Just recall, the Lagrangian function in this case was half m r dot square plus half m a plus r whole square theta dot square minus half k r plus m g by k. We have all done this earlier, so I am not explaining. I am just writing down so that we can start off from there. Plus, I will just illustrate something that students often make mistake. That is why I am doing this problem to its completion. Cos theta minus m g a. That is what. Just check.
So the third term will be r plus mg by k whole square.
Third term.
R plus mg by k whole square.
This is a square. That would be a square. Fine. Okay. So now you start writing the derivatives with respect to the two coordinates. The first derivative that you would write is Lagrangian with respect to r. When you write in terms of r, this has to be differentiated, this has to be differentiated, this has to be differentiated. So, how do you do it? You write it carefully. 2 comes forward, so it is m theta dot square a plus r differentiated, so it would be a plus r. Then so this one comes to this, then this one it will be minus k, this thing will remain r plus m g by k, and then from here plus m g cos theta. Done. MGA basically, okay, let it remain. So, this is with respect to r. Then with respect to r dot, what do you have? This remains. So, m r dot, enough. So, you can see from these two I can write down the first equation, and that would be d dt of dou Lagrangian dou r dot minus dou Lagrangian, it would be r equal to 0. So, substitute. The first term will come to m r double dot, no problem about it. Then the next term simply substituted, minus m theta dot square a plus r plus k r plus m g by k plus minus cos theta equal to 0. Done. First problem completed. Second, we write the same things with respect to theta. So, Lagrangian dou theta will be, well, this was the form, this vanishes, this vanishes, this vanishes, it is only here. So, it is pretty simple. What remains? Only this term. It would be, yeah, minus, because cos to sine, mg a plus r sin theta, that does it. Then this term is theta dot, बोलो क्या रहेगा? Yeah, simple. Okay. So, now we have to write the second equation, will be d dt of dot minus dou theta equal to 0. Now, this has to be differentiated. If you differentiate, what do you have? Yes. So, differentiate this with respect to this with respect to d dt, you have to take d dt. Since these are both variables, so you have to do it carefully. That is what I wanted to point out. So, you have by differentiating this, you have m a plus r whole square theta double dot plus then you differentiate this one. So, you have twice m theta dot a plus r into r dot, okay, minus, then it becomes plus, yes, m g a plus r sin theta equal to 0. Now, this is what students often, I found, in exams miss, that here that both these are time variables, and therefore, when you differentiate with respect to time, both have to be differentiated. That is what often people miss, and I have seen hundreds of answer scripts saying that this times theta double dot. No, it is not. That is one pointer, that is why I did this problem to its completion. So, these two are the differential equations of this system. So, second equation is this, first equation was this, clear. Notice that these equations are hopelessly nonlinear. Can you see? These are not linear equations really. So, in such simple systems also you are having nonlinear equation that we will deal with later. Now, okay, we need to talk about electrical circuits, because so far we are dealing with mechanical systems, but we started with saying in our earlier class that the electrical systems are equivalent to mechanical system. You can have almost exact equivalence. So, you might ask, then it should be possible to solve right equations for electrical circuits exactly the same way, right? Yes, that is true. But in that case, what were the steps? Steps were, step number 1 was that define the generalized coordinates that are consistent with the constants. In a mechanical system, it is easy to see the constants. A hanging ball with a wire, I can easily see the constant. But in electrical circuit, do you see the constant? Where is the constant? No, that is not, supply voltage is not the constant. Supply voltage is similar to a force, that is not a constant. The constant is essentially the way the circuit is wired up, circuit is connected. Some things are connected in series, means the two branch currents are forced to be the same, that is a constant. Two lines are connected in parallel, the voltages are forced to be the same, that is a constant. Okay. So, the point is that in electrical circuits the constants are the way the circuit is connected, that impose the constraints. But now our job is to define the minimum number of position coordinates, that is what we did in mechanical system. And what is the equivalent of position in electrical circuits? Charge. Okay. So, we have to deal with charge. Charge is equivalent to the position. So, charge becomes the configuration coordinate in an electrical circuit, but charge where? Again the rule was that I have to define the position coordinates, the minimum number of position coordinates that uniquely define the positional status of the system. That was what we did. In this case also we have to think in terms of, okay, the circuit is connected this way, what are the different charges that I need to consider as the minimum number of coordinates. Say, suppose the circuit is like this. Okay, there is an inductor, there is another inductor, there is a capacitor, there is a capacitor, and there is another capacitor. Then there is a charge flowing here, there is a charge flowing here, there is a charge flowing here, and what are the minimum number? Now, there anything could be taken as the minimum number, but from your first year knowledge of electrical circuits course, you probably have learnt that one simple possible solution to this problem is simply to consider the charges flowing in the loops, like so. At least it is guaranteed that there would be the minimum number of independent coordinates. That is what actually matters for us. So, let us say we will say Q1 is here, Q2 is here, simple. Q1 is here, Q2 is here. Say this is L1, this is L2. This is exactly why we did not write the Lagrangian as L as in written in many of the physics textbooks. We wrote it with a script L because we wanted to distinguish from the inductance, so that students do not get mixed up. C1, C2, C3. In this case also we will have to write down the kinetic energy and the potential energy. What is the equivalent of the kinetic energy in an electrical circuit? No, not the charge, the energy stored in the inductor, that is the equivalent of the kinetic energy, and the energy stored in the capacitor is the equivalent to a potential energy, because the capacitor has the character of being a compliant element equivalent to a spring, that is why we have to do it that way. So, if that is so, then you have your T in this case half L1 Q1 dot square. Q1 dot is nothing but the mesh current, okay, plus half L2 Q2 dot square. Fine. V, the potential energy, notice since we are writing the potential energy as V, all the potentials or applied electromotive forces we always will write as E, not V, because we do not want to have duplicity of notations. V is the charge energy stored here plus energy stored here plus the energy stored here. कितना energy इसमें है? How much is the energy here? 1 by 2 C1. Notice here the C is downstairs in the denominator. 1 by twice C1 into Q1 square plus 1 by twice C2. This fellow, how much is the charge flowing through this? Q1 minus Q2. Q1 minus Q2 square. How much is the energy stored here? 1 by 2 C3 Q2 square, right. When we have written the T and V this way, we can then write the Lagrangian as half L1 Q1 dot square plus half L2 Q2 dot square minus T minus V 1 by 2 C1 Q1 square minus 1 by 2 C2 Q1 minus Q2 square minus 1 by 2 C3 Q2 square. Now differentiate, same procedure. Strangely, you will notice that it is yielding exactly the same equation as this, is it not? See, here my, can you see all of them? Yes. Here my T is half L1 Q1 dot square, half M1 Q1 dot square, half L2 Q2 dot square, half M2 Q2 dot square, exactly the same, only M and L are interchanged. Therefore, the kinetic energy in these cases not only are conceptually the same, even in magnitude they are the same, if provided that you are expressing M and L in the same quantities, okay, whatever the units are. V half K1 Q1 square 1 by 2 C1 Q1 square half K3 Q2 square 1 by 2 C3 Q2 square, exactly the same, only K1 is equivalent to 1 by C1, K2 is equivalent to 1 by C2 and all that. And therefore, even without writing the differential equations here, I can tell pretty blindly that it will yield exactly the same differential equations as these that we have already obtained. Okay. So, I do not really need to write, because these two systems are equivalent of each other. These two systems are equivalent of each other. Equivalent in what sense? Equivalent in the following sense, that here what will happen if you say move this one and release it, it will oscillate, it will transfer the oscillation here, this fellow will also oscillate. So, there will be some dynamics, and the dynamics you will learn how to actually obtain the dynamics and plot it, but it is not difficult to see that there will be dynamics. Q1 and Q2 will vary, and you can draw the waveforms, Q1 and Q2. In this case, you are not really moving something and releasing. What would be the equivalent of moving M1 and releasing? What is the equivalent here? Yes, position is changed, which means the K1 is moved. K1 is moved means some energy stored initially in K1, which is equivalent to some charge being stored initially in C1. So, store some charge and switch it on, you will see that this system will also oscillate. The currents and voltages will also oscillate exactly the same way as this one. And then if the L1, L2 and C1, C2, C3 are numerically the same as these, they will have exactly the same dynamics. When its excursion, Q1's excursion reaches the maximum point, this current through the inductor, its or charge through the inductor, its excursion also reaches the same point. Exactly the same dynamics. That is why the electrical and mechanical system would be said to be system wise, not only element wise, system wise equivalent. Clear? Fine. So far we were considering systems that had only one type of potential, either it was a we have considered system with gravitational potential, all right. We have considered systems where the potential is represented by a spring and the energy is in spring. What about applied force? If there is an applied force, can it still be is still a conservative system. What was the definition of conservative system? We said that if you can write the force as minus the derivative of the potential function with respect to, if you can do that, then we said that it is a conservative system. Now, if you imagine here on this, suppose I am applying some kind of a force here, F. That force could be a sinusoidal forcing function or something like that, but somebody is applying a force here. Can that force be somehow included in this potential so that this is valid? Yes, that is true. That means even if there is a externally impressed force, then also the system is conservative in the sense that it can be expressed in this form. But how? In that case, the rule is that you have to add to the potential function force times the direction of the generalized coordinate, that particular generalized coordinate along which it is applied. So, in this case we will write V is equal to F times Q1 with a negative sign. Why? You will soon see that it is necessary in order to set the signs right. If we write it this way, the V due to the applied force is this much, then we have already written the rest of the V. We have already written the rest of the V function. We will only add if this is applied. Let us do it separately. Now, we are talking about a system where and there is a force applied here, F. Here this is Q1 and here is Q2. Then what? We have already written the rest of it. So, let me write V is equal to K1 Q1 square plus half K3 Q2 square plus half K2 Q1 minus Q2. This is there and this remains, sorry, square. This remains. What gets additionally added to this potential function, so that the total force is still obtainable from that potential function by simple derivative. What I said is that here you have to add minus F times Q1, that is it. If you do so, let us see what happens to the Lagrangian equation. The Lagrangian would be, the kinetic energy remains the same. So, I will directly write the Lagrangian. It was half m1 q1 dot square plus half m2 q2 dot square minus half k1 q1 square minus half k3 q2 square minus half k2 q1 minus q2 square plus f q1, right, because this is minus, it becomes plus. Now, when we write the Lagrangian with respect to q1, what do you have now? Here minus k1 q1, here what was it earlier? Let me just refer to that. Here earlier it was this, minus k2 q1 minus q2. Now, this will be added to that. So, it would be plus f, fine, but that will not happen if you differentiate with respect to q2. So, that remains the same, minus k3 q2 plus k2 q1 minus q2. Okay. Now, you write the first equation, first differential equation. These two remain the same as earlier. So, when we write the differential equations, it will be m1 q1 double dot as usual, but then this one has to be written. It will be plus k1 q1 plus k2 q1 minus q2 minus f equal to 0. See that the signs have been right, because this is mass into acceleration, this is the force applied on it by the springs, and this is the force applied externally. So, that is how the equation is written, which is right. The second equation remains exactly the same. It will be m2 q2 double dot plus k3 q2 minus k2 q1 minus q2 without any difference. So, it is trivial to take into account the external forces. What will happen if we want to do the same thing in an electrical circuit? External force is equivalent to a battery, a externally applied EMF. And what will be the equivalent of this? A force being applied in the q1 direction. What is equivalent to that? A source. Notice here. Here is the m1, which is equivalent to the L1, and what is the character of this force? This force shares the same velocity with m1, and in order for that to happen in the electrical circuit, you have to apply a battery here. That's it. So, if you really have a battery here and its applied voltage is E, in that case the equation and the process of derivation of the equation will exactly be the same. So, in that case what we will do? We will argue that here E is applied in the direction of the generalized coordinate q1, and therefore, with the V we will have minus E times q1. That is it. Clear? So, that is how we will write the differential equation. Fine. Let us solve a relatively difficult problem which has an applied force on it, and which is a very practically relevant problem. Slowly we are going into engineering problems. Have you seen ever launching of a spacecraft, a rocket for example? You must have seen in the TV, right? So, how does it happen? The spacecraft is launched, all right, but initially it has to be held there, and it is held there with the help of braces, right? So, if the braces are there and it fires, the whole thing will break off, right? So, that cannot be allowed. So, the braces have to come off. If it comes off, then the rocket will fall, right? So, how to prevent the rocket from falling? What happens is that down there is actually a vehicle like thing. There is actually a vehicle like thing which is allowed to move, and that moves and thereby keeps it vertical. It is like a inverted pendulum. The pendulum is vertical, and here this point is allowed to move, and it is actually a control system enabling which you keep it vertically and then you fire. That is why it remains vertical and then it goes off. That is how the rocket launching is normally done. And to model such a thing, let us model the inverted pendulum problem. Huh? So, inverted pendulum problem is where you have the base along with the wall, and there is a cart with wheels, and the pendulum is like this. Say, normally this could be a, mass could be uniformly distributed, but let us assume for our simplicity that this is a mass concentrated at the top, and here is another mass. This fellow also has mass, so let this be M1 and this fellow be M2, and then you have to apply force here in order for this to move and balance it. So, that force is F. Okay. Well, in this case, how would you define the generalized coordinates? There are two generalized coordinates. One, position of this fellow, which has to be measured simply from the wall. It can be measured from the wall. And this fellow's position can be measured in terms of the angle. Either you call this as q1 and this as q2, or if you want to retain the physical things theta, then let us call it x, then it would be easier, x and theta. But in our case, it is essentially q1 and q2, two position coordinates. Now, we are all set to write down the differential equation. So, the generalized coordinates in this case x and theta. Fine. Now, potential energy, the kinetic energy T. Kinetic energy would be a combination of the two kinetic energies, kinetic energy of this one and the kinetic energy of this one. For this one, it is simple, half m1 then x1 dot square, x dot square, done. For this one, it is a bit complicated because it has a circumferential motion. There is no radial motion, all right, but that circumferential motion has to be broken into two components, x and y, and x has this additional x dot added to it. There are two components really. So, the horizontal component is horizontal component of this motion. If this is L, then L theta dot is the circumferential motion. L theta dot cos theta would be horizontal component, and L theta dot sin theta would be the vertical component. The vertical component is unaffected by this motion. The horizontal component has this motion added to it. Simple. So, that way we can write down the T. Okay. So, what will it be? The horizontal component would be plus half m1 will m2, it would be L theta dot cos theta, L theta dot cos theta plus x dot, right. Yes, L theta dot cos theta is plus x, they add up square, plus half m2 L theta dot sin theta, L theta dot sin theta square. Oh, yes. this is the kinetic energy completed. Potential energy, potential energy are there because of two components. One, because of gravitational energy in M2, this does not have any gravitational energy, moves horizontally, but also there will be another component of the potential due to F, fine. So, what will be this quantity? It would be m g L cos theta. Now, F is being applied in the direction of x. X increases in this direction, F is also applied in this direction. So, it will be minus F x. Clear? What? M2, yes. Now, there will be a term here that will vanish. There will be one term coming out of this, that will be have cos square theta, and here is sin square theta, and they will add up to 1. So, this can be simplified. Just simplify that. So, let us write down the Lagrangian. Lagrangian is half m1 x dot square. Let us break that up. Half m2 L square theta dot square cos square theta plus half m2 x dot square plus half goes of m2 L theta dot cos theta x dot, right. I have broken up, just check if I have written correctly. I have just expanded the square, plus half m2 L theta dot, sorry, I will not write it, L square theta dot square sin square theta minus m2 G L cos theta plus f x. That is the total Lagrangian. Now, you notice that this fellow and this fellow, this term gets common, cos square plus sin square. So, I will just drop this term and drop this term. I can do that. So, it becomes relatively simpler expression for the Lagrangian. Now, we will need to take the derivative of the Lagrangian with respect to x. It will be, this goes off, this goes off, this goes off. Simple. Now, we have m1 x dot from here, this goes off here, this remains. So, plus m2 x dot, right. This one remains, but this is a complicated stuff, differentiate it properly. Plus m2 L theta dot cos theta, right. So, okay, let us write the other one before proceeding. No, let me write the equation from here. The equation would be then d dt of Lagrangian with respect to x dot minus Lagrangian with respect to x equal to 0. Now, when we expand it, it would be, write the d dt of this correctly, write the d dt of this correctly. Now, I am saying this because most students make a mistake here. write the ddt of this correctly. It will be m1 plus m2 x double dot plus
M2L cos theta theta double dot
yes m2l cos theta theta double dot minus
M2L sin theta.
right. Now we have to differentiate this m2l theta dot
Sin theta theta dot.
yeah sin theta theta dot square oh right. So this is the derivative of this. Now we have to write minus this, so that would be minus f equal to 0. Done. Next one, derivative of Lagrangian with respect to theta is, if you do it with respect to theta, can you see the expression? Yes, this goes off, this goes off, this goes off, this remains, this remains. So take the derivative correctly, it will be minus m2l theta dot sin theta x dot, fine. Plus m2gl sin theta, and with respect to theta dot is, this term remains, m2l square theta dot plus m2l cos theta x dot, right. Now again take the derivatives properly when you write this. Write it properly. Here we have this. The first term is simple, m2l square theta double dot, no problem here. Next term we will have problem, plus m2l cos theta x double dot minus m2l x dot sin theta theta dot. Then plus this one, so plus m2l theta dot sin theta x dot minus m2gl sin theta equal to 0. Does anything cancel off? No, third and the fourth. They cancel. M2l cancels off. So it is actually simpler equation, theta double dot L theta double dot plus cos theta x double dot minus g sin theta equal to 0. Does the other equation simplify? No. Okay. So that is the equation then. Good. So this is how the equations are to be written. Remember, this, if you try with any other method, would be enormously complicated, this particular problem. So that is why the strength of the Lagrangian approach becomes salient in this kind of problems. Okay. Thank you.